speaker is Eduardo Chillaron. He's Design and Engineering Manager at PVH. He has extensive knowledge and analysis of structure under wind loads. He has been working in the solar industry for over 10 years and joined PVH in that function in 2016. Eduardo, the floor is yours. Thank you.
Okay, thank you, Michael. Thanks a lot to all the attendants. Okay, let me share my screen. Okay, so yeah, thanks a lot. I'm going to talk about also about the new trend of these new models that we are having this year in the market, but more about how to improve adaptability and production of our trackers, of our plants with these new modules. You know, how to manage these and what's the challenges that we see from PVH and the solutions. Well, this is a brief summary of the points that we're going to talk. A brief introduction of PVH, just 2 slides. Just before current knowledge, what are the starting points for this new challenge? Why how are the new modules, and what are our solutions? Okay, our new trackers for these specific modules. Okay, so who we are? Well, as you know, PVH, we are a Spanish company. We're based in Valencia, where we have our factories. But, well, in any case, we have plants around the world in 5 continents, more than 190 plants, more than 70 plants higher than 50 megawatts, and more than 10 gigas supplied around the world. This is our product portfolio. Okay, we started the 2008 with a solar fixed structure and also with our Axon tracker, that it's a multi-row tracker. And this is the evolution of our product. Okay, in 2017 we launched our Monoline family trackers that are a single motor per row. And finally, the last product that we launched was this Axon Duo, a dual row tracker. Okay. Well, this is a brief introduction of PVH. Let's talk about now that we call, well, current knowledge, the starting points that we have to consider for this redesign challenge this year. Okay, this is something that we know that we are applying in all our trackers some years ago. No, first of all, it's the problem that we found more and more in the next projects. No, it's about the plant locations, the complicated slopes in all the new terrains for PV plants, and also the extreme weather conditions in some of them. No, so for that we have to take into account that we need trackers that are able to adapt to complicated terrains, and then can manage also the tracking to adapt to that, and also to can withstand higher winds. No, that's the main load of these that suffer this type of trackers. Regarding to the terrain adaptability, we implemented this tool that it's called Adaptive Attracting 3D. That finally that considers is the not only the X and Y coordinates of its tracker, also the elevation. So considering the height of the tracker that it's in front and in the rear, it's doing a backtracking to avoid shadows and to improve the production. Okay, this is something that we are applying to the trackers, to the tracking of our trackers. And regarding the production, well, finally, that we see is that, of course, bifacial modules are being implemented in most of the PV plants now around the world. So that we have a study, it's what is the gain, the bifacial gain that we have with the trackers, with the 1P trackers and with the 2P trackers, of course. We have both in our portfolio. So that we wanted to do here is to do an independent study to see what are the differences and to detect if some of them is better or not. No? So that we have done is to study the shadowing in the backside of the module, the effect of the mismatch due to this non-uniform backside irradiation, and finally to check what is the bifacial gain in 1P and in 2P, considering also the aspect ratio. That we have done, it's in our trackers, in the Axon Duo and in the Monoline 2P, do this test with several cells in one of the modules to check what is the relation that you can read in each position, okay? And after to obtain a comparison with that. That we see, here is an example in the left side of the screen. You can see the results that we obtained for the 1P tracker. Of course, we see like reduction in the gain due to in the radiation due to the shadow of the torque tube, and also a peak due to a reflection in the torque tube. And in the right side, we can see the same, but for the 2P tracker, okay? In this case, we see also an effect of the longer panel rail that is necessary to install for these modules, and well, also the effect of the torque tube. No? In any case, finally, these are the results, the conclusions that we have. Of course, well, you can see here the parameters that are, for example, needed to introduce to PVCs to calculate the production in the plant, okay? That we see is that, of course, for 1P, we have a bit worse results than for 2P in terms of structure shadow factor and in terms of mismatch in the rear side. But considering that the difference in temperature that we have seen between 1P and 2P is not, it's really low. It's not an important difference of temperature between two trackers. We see that due to the aspect ratio of both trackers, 1P and 2P, finally, the behavior or the beneficial gain of a 1P tracker about a 2P tracker is really similar, okay? That's the main conclusion of this study. So that we see is that a 2P tracker is a really good tracker for complicated terrains, okay? In terms of the production, it's similar for both. So for complicated terrains where it's necessary a good terrain adaptability or where the foundations are a problem, a good solution is the 2P trackers, okay? Well, so these are some points to consider in the new analysis that I'm going to show you later. Now I'm going to do a brief explanation about this new modules trend that also has a comment before Pedro, and what's the impact in both trackers, in both configurations, in 1P and in 2P. Well, as we have seen before, the new trend of modules is going to be to double the mass of the module from 20 kilos that could be in the past. Now sometimes it's close to 40. And well, the height is until 2.4, 2.5 meters, and the width until 1.3. It's a big change. Well, now that we see is that depending on the module supplier, there are different configurations for the trackers for 1P and for 2P due to the change in the number of modules per string, due to the change in the sizes. There is not homogeneous, okay? So we can see here several examples of the configuration of the 1P tracker that can go from maybe from 80 meters to 100 meters, depending on the configuration. And also in the 2P tracker, well, here we have put only one string. You can see the difference, but can move from 14 meters to 22 meters. But that we see is that, of course, it has an impact in the tracker. We are going to have longer trackers and with longer width, okay? Well, these are that we identify as the main tracker challenges in this year. No, first of all, it is necessary to do a redesign to adapt the trackers to these new modules. Okay, due to this change in the size, this big change is completely necessary to do a redesign from the wind tunnel test to the calculations. Okay, it's necessary to check all the design of the tracker again. From our point of view, it's really important to maintain and improve the terrain adaptability of the trackers. Even this increase in the length is necessary also to study about the increased production of these new trackers. Of course, to check compatibility, we are in contact with all the module suppliers to have compatibility of our trackers with the modules in terms of fixations of loads that the modules are receiving. Of course, maintain the solar plant safety, trying to maintain the cost or without any extra cost. For us, it is important to maintain both options, 1P and 2P, because depending on the plant, some of them could be the best. And of course, work also in the communications, because due to this new large size of modules, it could be a problem. No? Okay, so that's the introduction. Now let's go to see what from PVH we think is the solution for this new trend of modules. That we have done. We have launched to the market the new family of trackers called Monoline Plus, okay, in both configurations, 1P and 2P. These trackers are specific for these new ultra high power modules. Well, as an introduction, it's necessary, as I said before, a mechanical engineering. Why? I will comment only some points that I've listed here. The mass of the modules is higher. This reduces natural frequency, so we can have critical wind speeds lower. No, some problems of stability before than with previous trackers. Also, for the same reason, the tracker is longer, so we reduce the torsional stiffness, and the critical wind speed can be reduced. So we have high effects on aeroelastic critical wind speeds. We will have, of course, higher wind force and moments, but not only because we have a higher area, also because due to this increase in the size, we have higher adimensional coefficients. So we need to withstand higher loads than before in the module and also in the lock points in the sleeve drives. Well, so from PVH, we work with CPP. I think it's the laboratory is like the state of the art in the market, doing this aeroelastic wind tunnel test to verify that these new designs are still safe from a point of view of the aeroelastic phenomenons. Okay, so we check also 1P and 2P new configurations to check that this is not a problem for these new trackers. But not only aeroelastic, we have done again the static wind tunnel test to obtain these new adimensional coefficients and considering also the new dynamic amplification factors. Okay. Well, so we have done that, and we see that there is a different impact in 1P than in 2P trackers. In 1P, of course, we can reach a chord of 2.4 meters. Before it was around 2. But here the key is the length. No, we changed from trackers that previously were around 60 meters to trackers of 90 or 100 meters. The torsional stiffness and frequency is reduced, so we have to check what's the behavior of that against aeroelastic instabilities. Also collaborate with the solar model suppliers to validate fixations. But the other way in the 2P that we see is that we have a huge exposed area to the wind. It's the doubling chord. Some chords of the trackers can reach 5 meters and length, well, depending on the configuration, until 70. Okay, so what's that we have done? Well, this is the first version of this Monoline Plus, the 1P solution. For the 1P, we have launched our first 1P tracker with single motor per row. Okay, each row is moving independently from others. It can reach until around 100 meters. And that we have tried to do here, that we have done, is to improve the terrain adaptability, increasing the allowable slope in north-south direction. It can reach more than 20% with a new post head, and increase also the post installation tolerance. Okay, trying to avoid earthworks due to soil undulation. So we have increased this tolerance, this standard tolerance, to can do easy the installation of this tracker. To mitigate aeroelastic effects here, we have moved to a higher stow angle than before, okay, to maintain the stability and to maintain an operating wind speed higher. And of course, we have worked with main model suppliers in obtaining compatibility letters for this tracker. This is the 1P. Regarding the 2P, here, well, the problem is the double, more or less. No, we have here, we can reach a tracker until more than 70 meters. But the problem here is that we have a huge exposed area, no, a chord around 5 meters. So that we try to do is to move to a shallow stow angle close to 0 degrees, to reduce the efforts in the main steel components, to can launch a product that it's optimized in terms of steel and that it's safe enough. So that we have done is to add several lock points. No, we have add not only one SLIO drive in this tracker. Here we have 3 SLIO drives. Okay, this has been tested also with CPP. That we win here is that it's a more robust torque tube, a more robust tracker. Okay, we have increased the high torsional stiffness with these several lock points to can stow close to 0 degrees. But what happened here? Well, we are having a tracker that it's almost more than 70 meters. And as we have said before, we trust in the 2P for complicated terrains to can adapt to very well to these locations. So that we have done to obtain that, it's to well, to split mechanically this tracker. Okay, so then this is that we can do with this tracker. Okay, it's mechanically split in 3 with one main controller in the center. Okay, so it's one tracker from the control point of view, but it's split in 3 small tracker units. So with this, that we can do is to obtain a higher terrain adaptability around 23.5% in north-south slope, but each 20 meters. So it's really adaptable to a terrain. Also, we have reduced the installation cost because we have only to align 3 posts. So it's really easy to install. And also because the torque tube is only one member, we reduce the joints between torque tubes. So finally, it reduced the installation a lot. Also, regarding to the production, each string, each one of these small tracker units can move independently, can move in a different angle. So with our backtracking, with our 3D backtracking algorithm, we can do that each one can move without generate shadows to the backtracker. Okay, so each single string is moving to optimize the production, to increase the production. Okay. This is that I explained before. We have only one central controller to move the 3 SLIO drives. And regarding the backtracking 3D and regarding the movement of each single string, that we have done is the task of to compare what could be a long tracker of 70, 90, 100 meters. So these type of trackers that can be modular, but they must be installed with a linet or with only one torque tube. That we have compared with our simulations is that for complicated terrains, due to this tracker must be moved independent, but only one movement. It can generate shadows, so it's need to do hard backtracking. Comparing with our solution that it's adaptable and that you can adapt to a terrain, it's 20 meters, we can generate until 1% more of production, okay, due to this adaptation to a terrain and due to this specific movement of each single string to optimize the production. Finally, yeah, I would like to talk also about communications. We have higher modules, higher trackers, so maybe we can found interferences that can make a problem with this, that can interfere in the communication between the different trackers or the different control units. So that we have done is we work with LoRa. Okay, it's a long-range protocol that it's really useful for this, and then can avoid any problem with communications. Well, finally, just to show the conclusions of my presentation. First of all, and it's very important, with this new module strain, it's necessary to do a redesign of the tracker. Okay, the changes the changes in the module are affecting to a lot to the trackers, so it's necessary a redesign of wind tunnel test, of static checks, dynamic checks. Okay. Of course, that we continue collaboration with CPP. It's really important. It's a really expert wind tunnel laboratory to check all the points. We have launched this family of trackers that it's called Monoline Plus in 2 configurations, 1P and 2P. And we have increased the terrain adaptability a lot, and more with the 2P configuration. Okay, it's maybe the best tracker in terrain adaptability in the market. We work with this adaptive backtracking 3D that minimize the shadow losses. well, for a terrain with complex topology, the Monoline plus 2P provides additional benefit. And finally, that the long range and robust wireless communication with LoRa technology that we use avoids any problem with the communications. Okay, so yeah, that's all, Michael.
Eduardo, thanks a lot. I think I'm really happy that we did this event. I think it is at the right time. It's great to see you're all adapting to the challenges of these new modules. We have to speed up because thanks again. Please answer questions in the chat. I think there are some. Let's speed up because Philip